Thank you everyone for joining me today. Yes, today I'm going to give a very a kind of short talk about our recent research and already submitted paper on this topic. Yes, during my PhD, my research interest is focused on the underwater vehicles. So there's kind of some kind of underwater vehicle may have a cuboid shape. So we also did some theoretical study on flows past the cube. So today I'm bringing this topic is about the control of the supercritical bifurcations in the wake of the cube. And first of all, I think better to give a quick introduction about our previous results. About we already did a paper about this topic this year. It got published a couple months ago, and so we did the investigation about the lambda weeks transition phenomena, and so in that paper, we just established three different flow regimes. If we just put isolated and stationary cube in the constant streams, and this is a little bit different with the phenomenon in the wake of a sphere, and the three flow regimes, we call it OSS flow, PSS flow, and the HS flow. So for the OSS flow, this is short for orthogonal symmetry and steady flow, because this status the flow is steady and it has an orthogonal symmetry. If you got familiar with the group theory, people normally use the dihedral group D4 to describe this kind of symmetry. And as the Reynolds number is increased slightly higher, and the flow will transit to a planar symmetry steady, but the flow is still steady. So we call this one is a PSS flow. And supercritical hopeful application will occur for the Reynolds number above 255. And the regular helping vortex shedding can be observed in the saturated flow in this regime, but the planar symmetry is retained. And it's just inherited from the PSS flow. So if we observe the different vertical structures in these three different regimes, we can OSS flow. For the OSS flow, we have 4 pair of vortex tubes in the orthogonal symmetry, and the PSS flow is characterized by 2 strong opposite sign vortex tubes. Yeah, and for the HS flow, we can observe the regular happy vortex train, and it's noted that for each period, the upper branch and the lower branch have different shapes. So this corresponds to the distribution of the PSS flow, because if the HS flow will involve, if we just do the simulation from the 0 initial, the HS flow will involve starting initially into a PSS flow, and the periodicity is delayed after that phenomenon and grow relatively slower than that. So we were interested into the regular transitions. So we did a regular nonlinear stability analysis for the regular transition in our previous work. We just proposed a couple of pitchfork bifurcation model to address that regular transition problem. because that is a stationary bifurcation, we just hope we can find a good, well-defined mathematical expressions that can give us more information like the nature of the regular bifurcation. So these two equations are the model we proposed there. It's just simply based on the symmetry conditions in the HOSS flow, and we just assume that that regular bifurcation can be related to the lift coefficients, because that's a three-dimensional problem. We of course have three hydrodynamic coefficients, and we just assume the two lift coefficients in the y direction, CLY, and in z direction, CLZ, can be good enough to to model this question. And meanwhile, if we take the symmetry condition, we can give a unique Taylor series expansions, and we cut off, we omit the higher orders, and we go into this form. And so the coefficients in these two equations, we have K1, K2, and gamma. These coefficients can be determined by weakly nonlinear stability analysis, and by focusing on the dependence of these four quantities. Because we have a DNS result, then we can just consider the relation of those quantities numerically. So then we can determine the value of those coefficients, and we can obtain the bifurcation model. So this is the time histories of the lift coefficients for the case at radius number 210. The solid lines, blue one and the red ones, are the lift coefficients obtained by the DNS, and the dashed ones are the result from our model. We can see that with each other very perfectly. So coming with this bifurcation model, we can just consider what happened in the phase space. So in this case, if we can just do some calculation, and we will establish the equilibrium and the trajectories in the phase space like this, we can for that regular transition, we will have unstable fixed point in the middle of the coordinate. That's a red open circle, and we will calculate by our calculation. We will obtain another 4 stable fixed points, located along the horizontal and the vertical axis. Meanwhile, we also have 4 red points at the saddle fixed point. So that is the phase space of the coupled pitchfork bifurcation. So these results are basically our previous research. That research basically based on DNS. When we obtain this result, we feel that it is amazing, and the model is the result between the DNS and the model is very agreeable, very well. So we start to consider such a question: what's on Earth the transitional mechanism for the regular bifurcation? Because this is definitely a kind of unique thing, other than we haven't, to our best knowledge, we haven't seen such a thing before in other black bodies. So to satisfy our curiosities, it just leads us to the following work. We did a tree global linear stability analysis for this question. So the method we use to do the linear stability is the spectral element method. I think I put some basic knowledge about this method on this page. It's basically the alternative version of the finite element method. It's just instead of the piecewise polynomial functions, the SEM method use to kind of like model and nodal expansions to make simulate the function space within the element. So this is the method we use, and since we didn't actually give any changes to the regular routine to do such simulation, so we only just put it here very simply. The numerical simulation is we just employ a seventh order hierarchical that being polynomial expansion for the velocity field, and to solve the saddle point problem, we just config the eigenpair in the Tally-Hood base. That means the pressure expansion is sixth order. So this Jacobi polynomial is also orthogonality, and taking advantage of this orthogonality, we can reduce the condition number heavily for the pressure positive equation. So that's the key point why we can do the simulation for flow past such a three-dimensional block bodies with so many singularities. You can see the cube has sharp edges and vertices. So if we don't do those kind of modification, maybe it's very, very difficult to do the simulation. And for the base flow and the eigenvalue problem, we also put it here simply. For the regular transition, the base flow are calculated by the DNS ways in a confined computer domain. We just use a quarter of the full computer domain by just only preserve the positive y side and positive z-axis side, and we impose symmetry condition of the plan y equal to 0 and z equal to 0. After we obtained the OSD 1/4 base flow in this confined compute domain, we just projected onto the full compute domain according to the orthogonal symmetries. For the Hopf transition, we use the selective frequency damping method. The eigenvalue problem is solved with the Arnold iteration with exponential projection. In such a way, the most leading eigenvalue is the ones with the largest real part. Then we just need to calculate we just need to calculate the Arnold iteration once it gives us one of the converged eigenvalue. That's the eigenvalue that's the eigenvalue desired. So we don't need to do more calculations. So this is the result about the most unstable eigenfunction for the first three rows as a component of the perturbation velocity on some slices. And the last row is the isosurface of the derived streamwise vorticity. So we already obtained the and most unstable eigenfunction for the regular transition. And we are starting to consider about the transitional mechanism to think about how this regular transition occurs. Because if we just go back here and watch the area surface of the streamwise vorticity, we can see it consists of two parallel opposite sign streamwise vortex tubes, and it's along a particular direction if we focus on the rear view. So we think this is not a representative eigenfunction, because for the regular bifurcation, with the information we already obtained with the pitchfork bifurcation model, we can see the linear disturbance should grow in bounded within the unstable eigenspace. But if this is just the unique eigenspace eigenfunction for the transition, it cannot give it just cannot correspond to the pitchfork bifurcation, because we can see there are infinity numbers of trajectories in the phase space. So we suspect this is just the regular transition is have a multiple dimensional unstable eigenspace. This can be possible because we use the Arnold iteration to do the calculation. The Arnold calculation are based on the Krylov subspace. The dimension of this subspace is far smaller than the degree of freedom, and that means the geometry multiplicity can be larger than the algebra geometry when we solve the matrix, the eigenvalue problem. So we are trying to use a try and error procedure to identify the basis of the unstable eigenspace for the regular transition. So we noted that from the contour plots of the eigenspace, we just noted there are kind of similarities for the different velocity components. The uy on the plane y equal to 0 is almost the same with the uzy on the plane z equal to 0, just like the orange arrow. And the uy on the z equal to 0 is similar to uz on the y equal to 0. So we just, based on this information, we did some calculation, and we found the uy and uz are actually proportional to each other on these two slides. So we just can define a constant. So we can use this constant to represent this eigenfunction. So we use the ratio, the arctangent of the ratio uy and uz along the central line behind the cube. We can go to a theta as a constant for this one eigenfunction. And actually, if we just calculate the tangent direction of the streamwise vorticity in the rear view of the eigenfunction, we can find this direction is equal to this constant angle. So with this constant theta, we try to design a set of initial perturbations to do the linear stability analysis first of all, we just hope we can generate a set of well-defined initial perturbations. It can just lead us to obtain as much as possible eigenfunctions. And meanwhile, we just do not hope this set of initial perturbations give us a subspace of the a subspace of the unstable eigenspace. So we just use this equation to generate this set of initial perturbations. It's actually use a vector and at 0.5, negative 0.1 tangent theta and negative 0.1, and we rotate this vector by a small angle around the x-axis and plus Gaussian white noise. So this Gauss white noise can help us to avoid that situation. If we just rotate this vector around the x-axis, it might be span subspace of the. So we to avoid that situation, we have the Gauss white noise. And if we already have the initial perturbations, and we also need another set of initial basis functions to do the trial and error procedure. So we use this way to construct this initial basis. The first figure is the eigenfunction we obtained from the other iteration in our linear stability analysis. We just reflect this eigenfunction with respect to the time y equal to 0, we got the right one. And if we just plot these two eigenfunctions, we can obtain that one we marked as U plus with two horizontal parallel opposite sign vertex tubes. And if we minus that two eigenfunction, we can got another one. We mark it U minus. That's two vertical opposite sign vertex tubes. So by this construction, we will find the U plus and U minus are orthogonal to each other. And if we just normalize them, and we will get a set of orthogonal normalized basis functions. So the rest of the thing is just the way use that designed initial perturbation to generate a set of eigenfunction and test those eigenfunctions with the relations, the dependence of those eigenfunctions with the basis. So if we found it they are linearly dependent, then that means this basis can express that eigenfunction. But if we find another independent one, that means we just need to increase the dimension of our basis space. By this way, if we just give enough number of trials, we will establish the basis, the exact basis of the unstable eigenspace. So to measure the dependence, we define the residue by this way. So the left figure is the relation between the initial perturbations and the eigenfunction obtained based on the corresponding initial perturbations. We can see those plus signs and the open circles are they agree well with each other very well. That means that our design about the initial perturbations can eligibly give set of such eigenfunctions different with each other, then we can test the residual of those set of eigenfunctions with the basis. And the second figure is the value of the residue. We found for all the eigenfunctions, they all have a very, very small residue. That means the U plus and U minus are actually just the orthogonal and normalized base function for the unstable eigenspace of the regular transition. So we can give a general expression of the unstable eigenfunction as this. The eigenfunction can be constituted by the U plus and U minus with respect to angle theta. And of course, in such construction, the L2 norm is equal to 1. So the domain of the theta is from 0 to 2 pi, starting from y-axis and rotating around the x-axis counterclockwise. The following figure, we just give some examples by taking the value of theta in this set, and we can see for the different value of theta, we have different eigenfunction with its center region of the real view have the same orientations. In particular, if the theta equal to 3 pi or 2 minus that lowercase theta, that is just the eigenfunction we obtained by our first attempt of another iteration. So the following part is we just tested the effect of the linearity and the non-linearity in this regular transition. So if we just reconstruct the flow field by the base flow, here we use U bar and the eigenfunction in such a way, and compare the flow field with the result obtained by DNS. We can clearly observe as the time develops, the reconstructed field is so the first one is the base flow. The second one is the growth of the eigenspace. The third row is the reconstruction fields, and the last two rows are the DNS results. We can see the non-linearity part in the dashed we can see the nonlinear part by compare those values, those flow fields with the reconstruction flow fields. We will find the nonlinearity will stabilize the growth of the disturbance by just rotating those vortex tubes around the x-axis to the planar symmetry ones. So with the knowledge of the effects of the non-linearity, we can just give the control of the supercritical regular transition. So when the Reynolds number is above the critical value, so we can just use this reconstruction as initial perturbations to run the DNS. Then we will by give different value of the theta, we will control the saturated PSS flow to one of the four equivalent fixed points. Because the base flow is orthogonal symmetry, we can just divide they will spaced into four parts. So the principal growth angle, we can start from pi over 4 and 3 pi to 3 pi over 4. And this is just then we can go to a saturated PS flow in this pattern. And for different ranges of the principal growth angle, we will go to different saturated PSS flows. And the supercritical Hopf bifurcation can also be controlled by this way, because we have mentioned that the PSS flow, the PSS status is prior to the occurrence of the periodic vortex shedding, and the shedding will have correspondingly related to the posture of the PSS flow. Then we just use this way to control the flow growing to the corresponding PSS flows. That is just can develop into the corresponding vortex shedding status. Okay, so in this work, we just present a neat relation between the simple mathematics and the physics to understand how the radial transition occurs. It's just based on the linear combination of two eigentrays. So that explains why it can have infinity numbers of trajectories in the fixed space of the coupled pitchfork bifurcation model. And the linear combination of the eigenspace will determine the linear growth path, and the nonlinearity will only stabilize the growth afterwards. So, and we just think this kind of control ways, this ways to control the flow is kind of interesting. And of course, it's extensive work, because if we just have different flows with orthogonal symmetry, it is possible to encounter such a situation. Because, to our best knowledge, we haven't seen such a situation before, but we believe just we can dig it out in the future work. And yeah, so that is my presentation. Thank you.